Okay, so 1.6 is a very long section. There's tons of stuff in 1.6. It covers a lot of things all at once. And this is probably one of the hardest sections that you do this week. But this stuff is needed because you need to know how to solve various different types of equations, especially going on to pre-calc and calculus, you see all these different types of equations. And so you need to have at least some familiarity with how to solve them so that you're not caught unaware when you go on to further math classes. Plus, it's a good way to kind of get your critical thinking going because it's all about, okay, what type of equation do I have, and then what are the steps for solving? So it kind of teaches you a way to like focus on the type of equation versus just what it looks like and just, okay, have I seen an example like this? But you need to think about, is this rational? Is this radical? And then what are my steps? So 1.6 covers solving polynomial equations of degree 3 or higher. So we've solved quadratic, which is degree 2, and we've solved linear, which is degree 1. So now we're going to be looking at like something with an exponent of 3 or higher. Solving radical equations, so those will have square roots or cubed roots in them. Also, what falls under radical equations are rational exponents. So if it has an exponent of like 1/2 or 1/3. Solving rational equations, which are basically equations of fractions, and then absolute value equations, and then using nonlinear and non-quadratic models to solve real-life problems. So I'm going to be focusing on the first three. The real-life problems are in the textbook, but what you guys need more are the skills, and then you can look at those examples in the textbook to see how they're applied, but it's hard to apply them without having the skills first. So we're going to be focusing on the skills. So I'm going to start out with polynomial equations. So these are of the form where you have something x to some power plus something to some x to another power, like x squared plus x plus a number, or just, I mean, you can have x cubed, you can have x to the fourth. It's going to have an exponent on your variable of some number. So when you're solving polynomial equations, you basically have, at this point, you'll learn more options later on. When we get to week 5. But for now, you can solve by factoring out the greatest common factor, factoring by grouping, or taking like a square root or a cube root of the equation. And which method you use depends on what the equation looks like. The one thing that we never do when we're solving is divide by a variable, because you don't know what value your variable is. And if you're dividing by x and x is 0, then you're actually doing something you can't do because we can't divide by 0. So we never ever divide both sides by a variable. We can only divide both sides by a number. So there are tons of different types of polynomials out there, and I can't go through every single type you may see, but I'm going to try to go through at least one of each of the big types. So this is one that you would solve by factoring. And in this case, you would solve by factoring out the greatest common factor. So you factor the greatest common factor out when you see there's a variable in every single term. So if there's a variable in every term, that means you can at least factor out that variable. And then if you can factor out some numbers, that's awesome. So we are solving 36x cubed minus 100x equals 0. So I know I can factor out an x because I have an x in both terms. And then I'm trying to decide, can I factor out a number out of 36 and 100?
4.
So 4, that's exactly right. So that's the largest number that you can factor out. So we're going to factor out a 4x. So I'm going to have the 4x in front, and then I'm going to divide that out of each term. So 36 divided by 4 is 9, and then I'm removing an x, so I get x squared. And then 100 divided by 4 is 25, and then I remove the x. So first step was factoring out the greatest common factor, and now we're left with a quadratic. And so now we know what to do when we have this quadratic. You factor, or you can use the quadratic formula to solve each of these. In this particular case, this actually factors. This is a difference of two squares. This factors to 3x minus 5 times 3x plus 5. And so you factor, but you basically factor as far as you can go. And then once you've factored everything, you're using that zero product rule that we used when we're solving by factoring, and you're setting each factor equal to 0. So we have 4x equals 0, 3x minus 5 equal to 0, and 3x plus 5 equal to 0. So we're going to get 3 answers here, and you know how many answers you're going to get based off of the highest exponent. So in a quadratic, your exponent is 2, so you have 2 answers. A linear has an exponent of 1, so there's 1 answer. Here, our exponent was 3, so there's 3 answers. So if I solve 4x equals 0, I divide both sides by 4. That gives me x equals 0 as one answer. Then 3x minus 5 equals 0, so I'm going to add 5 to both sides to get 3x equals 5. And then I'm going to divide both sides by 3, and I'm going to get a fraction. I'm going to get x equals 5 thirds. So that is our second answer. And then the third equation, in this case, we're subtracting 5. So we have 3x equals negative 5. And then I divide both sides by 3. And I get x is equal to negative 5 thirds. So we get 3 answers here. So when you're solving a polynomial by factoring, you first, I'm going to do this in a different color here. You factor out the GCF, and then we factor the polynomial, or in fact the quadratic in this case, and then you set each factor equal to 0 and solve. And so that's the basic steps for solving a polynomial if you can factor. If you can't factor, there are some other things that you can try, but good for you guys is that you're going to be getting things in this class that generally are factorable, so that way you know that this is one of your options. Are there any questions on this example?
A pretty easy example.
Good. Now, I always say that there's going to be factoring every single week, and I'm not kidding. You're going to be factoring every single week. So by the end of this class, you guys should be factoring masters. Now, example 2. So this is when we're going to be factoring by grouping. So first, in order to solve any polynomial, you have to have the polynomial equal to 0. So I have to add that 6 to both sides so that I can have it equal to 0 on one side. So we get x cubed plus 2x squared plus 3x plus 6 equals 0. So we have 4 terms here, and there's no greatest common factor. I can't factor out an x because there's not an x in that last term, and there's no greatest common factor. So I can't do that method. But if I have 4 or more terms, I could attempt to factor by grouping. Usually we try factoring by grouping if there's 4 terms because it splits up easily. If you have more than 4 terms, it's a little harder. You have to kind of guess and check on how you split your groups up so that you have 2 groups. But whenever we're factoring in grouping, we group the first 2 things together and then the last 2 things together. And so what you do is you factor the GCF out of each group instead of the whole thing together. So
x squared out of the first one and then...
That's correct. So I can factor out x squared out of the first one, and then that leaves me with an x plus 2. And then I can factor 3 out of the second one, which leaves me with x plus 2. And then I still have this equals 0. Now, when you're factoring by grouping, you know you've done it right if you have in parentheses the same thing. So because I have x plus 2 in both sets of parentheses, I know I've done that together correctly. So what we essentially do is we factor again. We're factoring out that x plus 2. And then when I remove the x plus 2 from each term, I'm left with what's in front, the x squared plus 3. And then that equals 0. So now we have a quadratic there, and we say, okay, can I factor out x squared plus 3? Can I factor that? Well, that is not factorable. So if we can't factor that, that means we're going to have to use the quadratic formula or another method. But what we need to do is go to the step where we set each factor equal to 0. So I have x plus 2 equal to 0, and then x squared plus 3 equals 0. So I'm going to start with the x plus 2. I can solve that by subtracting 2 on both sides. We get x equals negative 2. Now the x squared plus 3, this is something that I can solve by taking square roots. So I can subtract 3 from both sides, which leaves me with x squared equals negative 3. And then I'm going to take the square root of both sides to cancel out my x squared. I'm going to just kind of move up here. So that leaves me with x, and then we always get a plus or minus when we're solving. And then I have the square root of negative 3. Now the square root of a negative, this is where we get complex numbers from 1.5. So that negative, I can pull that out to get an I. And I always like to put my I before the square root so that it doesn't look like it's in the square root. The book will put the I at the end, but then it kind of gets confusing. Is it in the square root? Is it not? So I always kind of put it in between so it doesn't get confusing. And so we got x equals plus or minus I times the square root of 3. And that actually gives us two answers here. And you can keep them in that form, or you can write them out with a positive I times the square root of 3 or a negative I times the square root of 3. But we do get two answers from there, and then we have the one answer with x equals negative 2. So that adds up to 3 solutions, which matches because our polynomial that we started at the beginning had the highest exponent being a 3. So we should end up with 3 solutions here. So are there any questions?
It was pretty easy as well. I remember doing some of these problems from high school, actually.
Good. I know we've got a lot of people that, some people were lucky enough not to take algebra in high school, and then they're like, I've never seen any of this. But if you've taken it in algebra, some of this should be familiar, or taken algebra in high school.
Yeah, I got all the way into pre-calculus, so.
So you're gonna in a good spot then. Okay, example 3. Now we're going to solve the polynomial by taking roots. So it's going to be like the one that I just did where I took the square root. But here we have x to the 6th. So we can't factor out a greatest common factor. And I can't factor this by grouping. It's only 2 terms, so that's not going to do anything. But we can set the x to the 6th by itself. So we're going to add 64 to both sides so that we get x to the 6th by itself, which is very similar to how we were solving something that was x squared plus or minus some number. Now, to undo x to the 6th, you take the 6th root. So like if it was x squared, we took the square root. Here we're taking the 6th root. So that's the root symbol with the 6 up there. And this is why we had to learn how to simplify radicals, because now we have something that we need to simplify here. So the 6th root cancels out the 6. I'm left with an x. And then when we have an even root, we get a plus or minus here. So I'm going to have a plus and a minus. And then I've got the 6th root of 64. So we want to try to simplify 64 by writing it as in its prime factorization form. And actually, let's see, I just did on my calculator, 2 to the 6th actually equals 64. So I'm going to rewrite this as plus or minus the 6th root of 2 to the 6th. So those 6's basically cancel, and so our answer is basically plus or minus square root of 2 for our answer for x. And so you may be wondering, well, wait a minute here. If our exponent is 6, we only get 2 answers here. We have a positive and a negative. Well, sometimes what you get are called double roots or triple roots, where you get the same answer more than once. And I'm actually going to pull up Desmos just to kind of show you this, to kind of show you how to check your answer. And this is actually not It's shown a little bit in this section, but they don't go into too much detail here. But, so I'm going to Desmos, our wonderful graphing calculator, and I'm going to type in x to the 6th minus 64. So our equation we're solving is where this is equal to 0. And so I'm going to zoom out so you can see the whole thing. And then modify the x-axis so it doesn't look so thin. There we go. So you can see that we're saying where does it equal 0? So that means where is x 0 or on the horizontal axis here, the x-axis. So there's 2 locations here. But what happens is, just because it's x to the 6th, there's this thing called the double root. And so even though there's 2 answers, when you solve, you end up with that answer more than once. And then, well, there's no point writing it more than once because it's the same number. So that's why we end up having 2 different answers, even though there are technically 6 possible answers. It's just that they are identical to each other, if that makes sense. But you can verify by graphing because you're looking for where is x equal to 0, or where is your equation equal to 0, which is on the x-axis, because basically if you set your equation equal to y, then you're saying where is y 0. So we're looking for these locations where the second value would be 0 and where it is on the x-axis, if that makes sense.
Sense to me.
Cool. So that's the third way to solve a polynomial, and if it's in some form where it's like x to some power plus or minus a number, then you would solve it by taking roots of, if it's whether the cubed root or 4th root or 5th root or whatever root you need to do. And I just noticed that when I take that 6th root, I said that would be a plus or minus 2, but I wrote the root symbol. That root symbol disappears. So I should not have written that symbol there. I don't want to confuse anybody with that. So some polynomials can't be solved by any of those methods that we've just seen. And so if possible, then what we do is we solve by substitution to kind of turn it into something that is quadratic. So you look at something, and I have the steps here, but it'd be a lot better just for me to walk through it, and then you can use these steps for reference. So here's an example where I can't use any of the other methods. So there's no greatest common factor to factor out of this. That's 3 terms, so I can't factor by grouping. And because I have 3 terms, I can't I can't solve by taking roots either. What makes this something that I can solve by substitution is you look at your exponents, and you want to make sure that your exponents that there's a pattern to how they're increasing. So you look at the middle term, which is x squared. So if you took that exponent, you multiply it by 2, you get the first term. And then basically if you remove 2 from the exponent, you get something without an exponent. So that's a special thing where you want to see a pattern to the exponents. Some additional ones would be if you had, oops, not the highlighter. Other things of this form would be if you had x to the 6th, x cubed plus some number. So you always want that highest exponent to be double the middle exponent, and then the third thing to have no exponent. And this only works if you have even exponents. So if it's an odd, you wouldn't be able to do this method. So you're looking for things that have even exponents. For the highest exponent is even, and then half of that exponent is the middle one, and then the third number has no exponent at all, basically. If it's in that form, then we can use this substitution thing. So what you do is you take your middle term and you do substitution. So we're going to let u equal x squared. Now, if I square both sides, then that means u squared would be x squared squared, which is x to the 4th. So this is why this is allowed to work, is because you take your middle term, set it equal to another variable, And then if you double that, you square that, that will get you your other one, so then you can substitute both things and get something quadratic. So when we do that, instead of x to the fourth, I'm going to use u squared minus 13, and then we set x squared is equal to u plus 36 equals 0. So we now have something that's quadratic, and now we know how to solve quadratic equations. We can solve them by factoring, completing the square. You can take square roots, not in this form though. You can solve it by the quadratic formula. The goal is to make a substitution so that it's something you know how to solve, which most of our things that we do with substitution, we're either turning it into something linear or something quadratic. And with polynomials that we solve this way, we always turn them quadratic. So u squared minus 13u plus 36, this is something that factors. So this factors to u minus 9, u minus 4. Since a negative 9 times negative 4 is a positive 36, and negative 9 minus 4 gives you a negative 13. So we're going to keep solving. We're going to be solving for u instead of x. So I set each factor equal to 0. So I have u minus 9 equal to 0, u minus 4 equal to 0. And then when I add 9 to both sides, I get u is equal to 9. And then add 4 to both sides, u is equal to 4. But our original problem is not u. Our original problem is x squared. So we want to actually replace u back with x squared, because we set u equal to x squared. So now I'm going to say, okay, I really have x squared equals 9 and x squared equals 4. And then you're going to solve both of those for x. So I'm going to take these and go up here. So I have x squared equals 9 and x squared equals 4. So you want to take the square root of both sides so that you can solve for x. And remember, we're going to get a plus or minus. So the square root of 9 is 3. So I got x equals plus or minus 3. And then when I take the square root of 4, I got x equals plus or minus 2. And I actually have 4 answers here because we started with x to the fourth as the highest power. So we should have 4 solutions or less if one of them repeats. But we do have 4 solutions. We have a positive and a negative 3, and then a positive and a negative 2. So the trick is you want to do some sort of substitution so that you make it quadratic. And then we know how to solve the quadratic equation. And one thing I really want to, if there's anything that you learn from this section, it's like everything is going to eventually turn linear or quadratic, because those are the two basics. Those are the two most important ways to solve. If you can solve linear and quadratic equations, then you can manipulate things to put them in those forms so that you know how to solve.
Sounds good. No questions for me yet.
Yeah, and I think everybody else popped off. So I think you are. We must have scared everybody else away, or maybe they're like, you know what? I'll just watch the recording. Maybe they're like, I can't factor this fast. Oh, and we just had somebody join. So, hi Ryan, welcome. I was just saying that we scared everyone else away, but I'm glad that somebody is not scared away yet. So we just finished solving polynomials, and now we're going to move on to radical equations. So these are the ones that have square roots, cubed roots. They could have fourth roots, fifth roots. They could have fractions and your exponent. They all kind of fit underneath this bucket. So when you're solving one of these, what you want to do is get the radical symbol by itself. You're going to try to do that, and if it has a number in front of it, you're going to have to divide both sides by that number because you just want it by itself. And then what you do is you undo it. So if it's a square root, you square. If it's a cubed root, you cube. So you're going to do the reverse operation to undo the symbol. Then you're going to end up with something that's linear or quadratic, and then you solve using our methods for that. And we always have to check our answers because we get what are called extraneous solutions. They're basically extra solutions, because whenever you're squaring something, you're taking something that maybe had one solution and now you're creating two solutions. So while I didn't check my answers for any of the polynomial ones, you do need to check your answers for radical equations, because you do create solutions that aren't solutions to the original problem. So these take a little more time because you have to check your work. So I'm going to start with one that has a square root. So we need to get the square root by itself, and I have this equal to 0. The easiest way to get the square root by itself is to actually add 2 square root of x to both sides instead of subtracting the 6. And I do that just because I like to have positives on, in front of my variables and stuff. Whoops, I meant to write a plus instead of an equal sign there. So if I subtracted 6, then I just have negatives, and whenever possible, I try to get rid of those so I can have positives. So we have 6 equals 2 times the square root of x. Now I want that x, or the square root of x, by itself, so I need to get rid of that 2 in front. That is 2 times the square root of x, so we're going to divide both sides by 2. So 6 divided by 2 is 3. So I have 3 times the square root of x. Now I need to undo the square root. And so we do this by squaring both sides. And this is a process that's going to result in extra solutions. So 3 squared is 9. So we get 9 is equal to x. Now in this case, we have one solution. So sometimes it's possible to solve and you end up with no solutions if this ended up being an extra solution. So we need to check that x equals 9 actually works in this equation, because if it doesn't, then we have no solution. So these equations actually tend to show up with no solutions much more than other types of equations. So you have to watch out for that if you get something that doesn't work, that doesn't necessarily mean you messed up. It could mean there's no solution. So I'm going to check my work, check my answer, just to see if it works or not. So 6 minus 2 times the square root, and then instead of x, I'm going to write 9 equals 0. So the square root of 9 is 3, so this is going to be 6 minus 2 times 3 equals 0. 2 times 3 is 6, so we get 6 minus 6 equals 0, which gives us 0 equals 0. Our answer checks out because we get something that's true. So in this case, we got lucky. We didn't have any extra solutions, and so our solution that we found is the correct answer. So sometimes you get extras. Are there any questions?
When we are doing our homework, do we need to put the check for our homework assignment?
We're not going to be looking for the check in your homework assignment, so if you don't want to bother writing that, but you definitely want to do the check just to make sure that you don't have the wrong answer, especially like on a quiz and you're solving one of these, because frequently on the quiz they're multiple choice, and one of the options will have like both answers, like if you get 2 answers and maybe one of them is extra and the real answer is one of them. So you definitely want to check for the quiz. But on the homework, you don't have to write this down, because what we're caring about the homework is we're just checking, okay, did you get the right answer? Because you can use tutor.com to make sure you're doing the work and all that kind of stuff.
But then that'll get you in the rhythm of doing it anyway, so that way you can always check your answers anyway. So. Yes, yeah. So I mean, definitely, I would do it anyway. But I know some people they don't want to have to, write all that work. So it's not required. It's recommended. So example here, now we have a cubed root. So this one you're going to have, to undo a cube your thing. So again, we need to get that cubed root by itself. And so I'm going to do this by adding 3 to both sides. So the cubed root of 12 minus x equal to 3. So in order to undo the cubed root,
we're going to cube both sides. So when you cube that, you get what's underneath, 12 minus x, and then 3 to the third power is 27. So we have 12 minus x equals 27. So now you have something linear. Everything always goes back to a quadratic or a linear equation in the end. So now we have a linear equation that we can solve for x. So I'm going to subtract 12 from both sides. And don't forget that negative in front of the x. I see a lot of people drop negatives. It's very important to make sure you include the negative if there's a negative in front. And then 27 minus 12 gives you 15. So then I'm going to divide both sides by -1, which gives me x is equal to -15. Now we need to check our answer. So I need to plug this into our original problem. For the cubed root of 12 minus -15 minus 3 equals 0. So 12 minus a -15, that's 12 plus 15, so that gets us back to 27. So we have the cubed root of 27 minus 3 equals 0. Cubed root of 27 is 3, so we get 3 minus 3 equals 0, which works out to 0 equals 0. So this checks out, and so that is our answer. Now a little tip. When you're looking to see whether you have extra solutions or not, it depends on what's underneath the radical symbol. If you have something linear underneath the radical symbol, you should have one solution. So we had something linear at 12 minus x, that's linear, under the symbol, so we should have one solution. So generally what that means is if you got one solution when you solved, it's going to check out. If somehow when we were solving we ended up with something squared and we ended up with two solutions, then one of those won't check out because it's linear underneath the symbol. The same thing here. So we had just x, so that's linear. So we should have one solution. If we had ended up with more than one, then one of them wouldn't have worked out. I've never actually seen this rule written down anywhere, but I've never had it disproved in all the many times that I've solved. So this is my, I don't want to say that it's a hard and fast rule because I've never actually seen it taught anywhere, and I don't want to teach you guys something that maybe there's one case where it doesn't work out, but I have not seen it disproved. So that's basically a rule of thumb that I use to determine, to double check myself. Okay, it's linear, I should get one solution here. So are there any questions on the cubed root?
I find it pretty easy so far.
Okay. Now the next one here, so this has a rational exponent. It still falls underneath a radical because anything where you're having a fraction in your exponent, those can be rewritten as radical equations. And my guiding rule here still applies. So I have x plus 2 in the parentheses, so we should have one solution here because that's linear. So when you're solving something like this, you need to get the rational exponent by itself. In this case, it's already by itself, so we don't have to do anything extra. And what you want to do is undo by taking it to the power of the reciprocal. So in these cases, you're going to take the reciprocal. You're going to raise it to the reciprocal power. So the exponent is 2/3, so we're going to raise it to the 3/2 power. And that works out because when you multiply those fractions, we have 2/3, and when you multiply your exponents, so it would be times 3/2, we get 6/6, which equals 1. So that's how that cancels out. So I'm left with x plus 2 equals 9 to the 3/2 power. Now we need to simplify 9 to the 3/2. So I, whenever possible, try to separate it out so that I have the fraction part and then I do the numerator there. So I can split the 3/2 to 1/2 times 3. And I'm going to do the 1/2 part. So that 1/2, that means we're taking the square root of 9. because the square root is actually the same thing as a 1/2 power. And I see that I wrote an extra equal sign. That should be x plus 2. Yeah, Davis, do you have a question?
Yeah, I'm sorry, guys. I just joined right now because I'm from work. So, where did you get one of the half? Because I just want to understand where you got the half. It's
So
like
we
9, yeah,
we have the 3 halves. So I'm splitting this. So I have 3 halves, and I can split that up as 2 fractions multiplied by each other, and I'm basically splitting them up and then putting ones in the other direction. And 3 over 1 is just equal to 3. So this is the same thing as 3 times 1/2. And so then what I'm doing is, our rule of exponents are that if you have an exponent and then another exponent outside there, you multiply. And so I'm just undoing that process, and I'm doing it specifically so that I have the 1/2 part, the fraction part, on the inside, and then the whole number on the outside. Does that help?
yeah.
Okay.
Yeah.
If you have more questions or you're still confused, let me know.
It's all right, no problem.
Okay. So we have this 9 to the 1/2 power, so that's the same thing as taking the square root. So I'm going to take the square root of 9, which gives us 3. So I'm going to have x plus 2 equals 3 to the 3rd power. So then I'm going to do 3 to the 3rd power.
I think what he didn't get is that you're actually kind of factoring out a 1/2 to your 3 over 2, and then using your 1/2 on the inside and then your 3 on the outside.
Yeah, you can think of it as that. Yeah, you can think of it as factoring out that 1/2. That's another way to explain it. So hopefully that other alternate explanation helps. This actually comes from back in P.2 when it was talking about the rules of like radicals, and we were talking about all these radicals and rational exponents, and there's actually a rule that says you can split those up. So you can always double check P.2 as well on that. So back to, yes, is there another question?
Yeah, so I was thinking here, sorry, on the top where I see like x plus 2 exponent 2 over 3, because I was thinking like you can say it's like x plus 2 exponent 2 and radical 3, kind of 3 radical,
Yes.
and then equals to 9. So I don't know if that's what I was thinking. And probably we can do like a 3 exponent 2, the one that gives us like 9. I don't know.
Yeah, you can. Yeah, that you can definitely do that. And if you did that on the left with the x plus 2, it's actually a lot more complicated to solve it that way. So which is why I didn't do that. But you could take this 9 to the 3 halves, and you can turn this into 9 cubed and then the square root. That's the same thing.
Oh, okay.
And actually, you're allowed to rearrange those. So you could do 9 squared and then whoops, 9 square root and then cube it. And that's essentially what I'm doing. I'm just writing it as a fraction exponent instead of the square root symbol. So either one of those, you'll get the same answer. I decided to do the square root first because it makes it smaller, because 9 cubed is a giant number, and I'd rather cube something smaller. So that's why I did it that way.
Bye.
Are there any other questions before I move on this problem?
For me, I'm
okay. So we've got x plus 2 equals 3 cubed. So 3 cubed is equal to 27. So I have x plus 2 equals 27. So I'm going to subtract 2 from both sides, which gives us x is equal to 25. Now we do want to check our answer here This should be the solution because, as I said, we're looking for one solution. We got one answer here, but we should always check. So I'm going to plug that in. So in parentheses, we have x plus 2. So it's going to be 25 plus 2 to the 2/3 power, and we're hoping we're going to get 9 out. So 25 plus 2 is 27. And I'm going to just do 27 2/3 power in my calculator, because if you just want to make sure that your calculator, if you're going to do that, you need to put parentheses around the 2/3 to make sure that it's doing it correctly. But you do get 9. So we get 9 equal to 9, which means that our answer does check. So x in this case is 25. Are there any other questions?
A question.
Yeah.
You have 9 to the half. I thought that would be like 4.5 instead of, you know what I mean? Because you got 27 to the 2/3, which would be 9, 3 times 3 times 3. Why would it be 9 to the half would be 3? I don't get that.
So it's 9 to the 1/2 power. So that 1/2 power is the same thing as the square root. So it's not 9 divided by 1/2.
I see what you're saying.
Yeah. And so the same thing, like the 2/3 power is not times 2 divided by 3. It's actually, those are all in the exponents. The top of the fraction you're squaring if it's 2, and then the bottom you're doing a root. So that would be like a cubed root.
Thank you for clarifying.
Yeah. So that's the 2/3, the 3/2. A lot of people get really confused with these whole rational exponents things, and it's like if you have a fraction in your exponent, the top is like a regular exponent, and the bottom of the fraction is always the root. There are other questions? Okay. Next up, rational equations. So these are where you have a fraction, and you've actually seen some of these in 1.2, but all of those were designed so that when you solve them, you got linear equations out. Now we're going to be doing rational equations where you might get quadratics out, and then you need to solve using the methods of a quadratic. But the steps are the same as what you saw in 1.2. You need to get a common denominator. Then you make sure that each fraction has that common denominator, so you have to multiply the fractions by what's missing. Then you multiply both sides of the equation by the denominator so that it cancels out. And then you simplify and you go ahead and solve based off of whether you get a linear or quadratic out. Everything always goes back to linear or quadratic. And the most important thing, and I'll admit I forget to do this, because you do have to always check to make sure that none of your answers are making the denominator 0. So you have to check to make sure that it's in the domain and you're not dividing by 0, because you could get solutions that then are extra solutions because you end up dividing by 0, and we can't have those. So rational equations are another one where you might end up with having no solutions depending on how it solves. So here I'm starting with a simple one where we just have x, 3, and 6 in our denominator. And so we want to get a common denominator here. And what I do, the way I do this, is if I have fractions on both sides, I get a common denominator with just the left side and combine those. So that way I can multiply, do a kind of treat it like a proportion where you can cross multiply. But I only do that if it's like really simple, like there's just an x and a 3. If I have things in the denominator like x plus 2 or x minus 5 or something more complicated, then I won't do that method. But here, these are simple enough that I would try to make this a proportion so that I can just cross multiply. So what that means is I'm going to get the left side to have a common denominator, which would be 3x. So I'm actually going to do this in another color. So my first fraction is 4 over x, and I want my denominator to have a 3. So I need to multiply the top and the bottom by 3. Second fraction on the left side, I don't have an x, so I need to multiply the top and the bottom by x. And then I'm going to leave the one on the right alone. So 3 times 4 is 12, so I have 12 over 3x minus then 5x over 3x equals x over 6. Now I'm going to combine the fractions. I'm going to subtract those. So I'm going to combine those into 12 minus 5x, that's on the left, over 3x equals x over 6. If you have a fraction equals a fraction, that's a proportion, and that's where you multiply. You can cross multiply, which means multiplying the diagonals together. So I'd multiply one diagonal, which would be 3x times x. So I'm actually going to write that out. I usually multiply this in my head, but I'm going to actually write that step. And then you multiply the other diagonal together, the 12 minus 5x times the 6. So I'm going to put the 6 in front, and then we're distributing here. That's going to be that 6 is multiplied by 12 minus 5x, that whole thing. So I'm going to simplify both sides. So 3x times x is 3x squared. And then I'm going to distribute on the right. So 6 times 12 is 72. 6 times negative 5 is negative 30. So I have 72 minus 30x on the right. So now when you see that you have a quadratic, as soon as you get that x squared, that means we need to solve a quadratic equation. So that means get everything on one side so that it's equal to 0. And then it means you're going to either factor or use the quadratic formula, basically. Nobody usually solves by completing the square. I always like to have my 3x squared, whatever the x squared thing, be positive. So I'm going to move the 72 and the 30. So I'm going to be subtracting 72 from both sides and adding 30 to both sides, which gets me 3x squared plus 30x minus 72 equals 0, because I just like to have that positive coefficient in front of the x squared. Now there's a greatest common factor here, because I can divide 3 out of 3, 30, and 72. So I'm going to factor out that 3. So I have x squared plus, and then 30 divided by 3 is 10. And then 72 divided by 3 should be 24. Yep, so I got minus 24 equal to 0. So x squared plus 10x minus 24, this is factorable. So I'm going to factor this. So this factors to x plus 12, x minus 2. 12 times negative 2 gets you negative 24. 12 minus 2 gets you that positive 10. So now we're going to set each factor equal to 0. And I don't have to worry about the 3, because 3 equals 0 just doesn't mean anything. So I have x plus 12 equal to 0, x minus 2 equal to 0. So this gives me x is equal to negative 12 and x is equal to 2. And then I just need to double check back in the original problem that neither of those numbers make the denominator 0. In our original problem, our domain, the only thing we had to worry about is that x cannot equal 0, because that's the only variable in the denominator. So since we did not get x equals 0 as one of our answers, both of these values work. And so we have two solutions to this rational equation, negative 12 and 2.
What do we do with that leftover 3 there?
The 3 doesn't mean anything, basically, because it doesn't have a variable. I could, once I'm at that quadratic, I could divide both sides by 3 and it disappears. It's basically doesn't mean anything when you're solving. There are other questions?
Did you get the x does not equal 0 again?
And why you would have
That comes from our denominator, where we have, oops, that was not the highlighter. We have x here. So the denominator can't equal 0. So since I have x in the denominator, that means x cannot equal 0.
Sounds good.
Are there any other questions? Yes.
Yeah, the question I have, so you cannot give because the way you added, like let's see where you put x, you added 3 and x on one side. How about this? I mean, to the right side where there's a x in the bottom of 6. So you cannot find like the same denominator, whatever. You cannot find it.
I could. If I wanted to, I could make everything have a denominator of, say, 6x. But in this case, I didn't really need to, because as long as I ended up with the same denominator and I could combine, so I just had a fraction equals a fraction, then all I have to do is multiply the diagonals together. And I think that's a little bit easier than trying to get everything on all sides to have the same denominator.
Okay.
But you could do it that way. You'll get the same answer in the end. There's multiple ways to solve these problems, and this is just the way that I think is more efficient for the way I think. So that's why I'm demonstrating it this way.
You say like x is not equal to 0. I have a confusion on that. Like, how do you know that this x is not equal to 0 or x is equal to 0?
So this comes from the domain. So whenever we have fractions, we can never divide by 0. And so we don't know what x is in the original problem, but we know we have x in the denominator in the bottom of the fraction, which means that we're dividing by x. So because I can't divide by 0, that means that x down there can't be equal to 0. Because if it is, if I plugged in 0 there, then I'd have 4 divided by 0, which we can't do. So that's just saying that whatever we find for x in the end, we can't get 0, because otherwise it's not going to work in the equation.
So are you checking for denominator or you checking on numerator?
It's always the denominator, so that's why I highlighted
Okay.
the x. Yeah, it's always the denominator cannot equal 0.
Oh, okay.
There are other questions? Okay. Now here's another one with a rational equation. So again, this is one where I usually try to get the left side to have a common denominator and then the right side have a common denominator. I don't try to get both sides to have a common denominator. So we have 4 over x plus 1 minus 3 times x plus 2. And so I'm going to multiply each fraction by the other denominator. So like I'm going to multiply the first fraction by x plus 2 on the top and the bottom. And then the second fraction, and I'm going to make sure I'm going to write this correct. The second fraction will be multiplied by the x plus 1 on the top and the bottom. So this will give me 4 times x plus 2, and then my denominator is x plus 2 times x plus 1 minus 3 times x plus 1 over x plus 2 times x plus 1 equal to 1. So in order to combine the fractions on the left, I need to first distribute. So I need to do the 4 times the x plus 2. So 4 times x is 4x, and then 4 times 2 is 8. So I have 4x plus 8 over x plus 2 times x plus 1 minus, then I distribute the 3 through the parentheses, so that gives me 3x plus 3, and then x plus 2 times x plus 1 equals 1. Now I'm going to combine these fractions, and a very common error people do when subtracting, if they're subtracting something with multiple terms on the top, is they mess up their signs. So what I do is I take the subtraction, I turn it to a plus, and then I change the signs of everything to the right of that subtraction, because you're subtracting everything there. And that makes it, you're less likely to make mistakes if you do that. So you turn that minus into a plus, but then you change the signs on the top of everything that's to the right of that subtraction. So now I'm going to combine. I have 4x plus negative 3, which is x. 8 plus negative 3, which is 5. And then x plus 2 times x plus 1 equals 1. Now, I want to get rid of my denominator. And since I just have a whole number on the right, there's no need to cross multiply. I'm just going to multiply both sides by the denominator. So I'm going to multiply the left by x plus 2 times x plus 1. And then the right by x plus 2 times x plus 1. So that leaves me, the fraction will cancel out, and I have x plus 5. And then that 1 isn't really doing anything because 1 times anything is just the same thing. So I'm going to FOIL. I'm going to multiply out the x plus 2 times the x plus 1. So that gives me x squared. And then I get a plus 2x plus 1, so that's plus 3x plus 2 times 1 is 2. So, yes.
So I have another question about if you have, for example, like x plus 6 over like x plus 12 equals to 0. So how do you do that? So do you do almost the same thing like here?
Yes. You would do the same thing. And what would happen if it's equal to 0, 0 times anything is 0, so you'd end up with only 0 on the right.
Oh, means the denominator doesn't count at that time if that's the case. Because if we're going to have the same denominator, means that denominator going to be canceled out with the one you have there, and it'll be multiplied to 0, and it'll be 0, right?
Yes, yeah. So writing it up on the top right here, if I multiply both sides by x plus 12, 0 times anything is 0. So you end up with, if I can get my black, just x plus 6 equals 0. But since ours is 1, it didn't cancel out, but the 1 just, well, at least we don't have to multiply by another number. We can just FOIL out what we have.
Or can I ask you, I'm sorry because I came late. So there's the question I had another. It was about almost the thing that you just finished. Was it like when you have the number before radical, and inside you have probably like x plus 10 and plus any number equals to 0. So what happened to that number that comes before radical? So do you also include in parentheses and put a square on it? So
I actually did an example here, for example 5.
Oh, okay, yeah, that's like
so that. Yeah. So what you do is you want to remove that number from the radical before you square or cube or anything.
How do you remove that? I'm so sorry to take you back because I did not catch. I just came when this was already done.
Yeah, so if it's like 2 or 3 times some radical, you divide that by that number because it's multiplied. So you divide to get rid of it.
So you divide the same number?
Mm-hmm.
I'm sorry. It's okay.
Yeah, I am recording this, so you will be able to watch the recording so you can watch everything you missed afterwards.
Oh, okay, no problem. Thank you.
All right. So, all right, going back. Nope, not the right one. Hold on. All right. So, do we have any questions so far on where I'm at on this rational one?
Yeah.
Okay. So, I have this x plus 5 equals x squared plus 3x plus 2. So now, again, I have a quadratic, so I need to get everything on one side so that I can either use quadratic formula or factor. and I like to have a positive x squared. So I'm going to move the x plus 5. I'm going to subtract the x and subtract the 5 so that those are on the right side. So I'm going to subtract the x and subtract the 5, and then I'm going to move up. So I get 0 equals x squared minus 4x minus 3. 3 minus 2 is not 4x. Or 3 minus 1 is not 4x. I need to double check my arithmetic. That should be plus 2x minus 3. For some reason, I was thinking that was minus 3 there. Okay. Now this is another one. Let's see. We can factor this. So I'm going to factor. So this factors to x plus 3 times x minus 1. So 3 times negative 1 gives us our negative 3. 3 minus 1 gives us our 2. So now we're going to solve each factor. So we're going to set them equal to 0. So I have x plus 3 equals 0, x minus 1 equal to 0, and then I solve. So I got x is equal to negative 3, x is equal to 1. And then we need to double check that we're not making the denominator equal to 0. So in my denominator, I'm going to just write these here. The denominator, we have two things. We have x plus 1 and x plus 2. So we need to make sure that if I plug in negative 3 or 1 into either of those, I'm not getting 0. So if I plug negative 3 into x plus 1, I get negative 2, so that's not 0. And negative 3 plus 2 gives me negative 1, so that's still not 0. And then if I plug x equals 1, 1 plus 1 is 2, and 1 plus 2 is 3. So neither of my values for x make the denominator 0. So I don't have to, can't exclude those. Those numbers both work, because none of them will make the denominator 0.
Any number that makes a denominator 0, it's not correct.
Yes. Yes. And it's generally the number that's the opposite of the sign here. So like one of the denominators was x plus 1, so that means x can't be negative 1. And then we got x plus 2, so that means x can't be negative 2. So as long as you don't get those two numbers, anything you get will work. Any other questions?
Good.
Okay. Now, last type of equation. There's a lot of things in this section. Absolute value equations. So those are, you've got these vertical bars equal to something. So absolute value equations, they always turn into two different equations that you're solving. So you generally always have two solutions for an absolute value equation, because what's inside the absolute value could be positive or negative, and you'll get the same thing out because it basically turns every negative positive. So to solve these, you first have to get the absolute value part by itself, and then you create two equations. One of them where the inside is equal to the outside, and then another one where the inside is equal to the opposite side of what is on the outside. And then you solve each of those for x. And always, again, check your answers, because sometimes you do end up with extra solutions, especially with the absolute value inequalities, which is in a later section. So you do always want to check your work just to be safe. So solve an absolute value equation here. So I've got the absolute value of 3x plus 2 equals 7. So I've got the absolute value by itself. So I'm going to create two equations. One of them where I just ignore the absolute value and I have 3x plus 2 equals 7. But then another one where you have 3x plus 2 equal to the opposite of what's on the outside of the symbol. So instead of a positive 7, I'm going to take the opposite, which is a negative 7. So this creates two equations, one with positive 7, one with negative 7. Then you solve both of these for x. So if I solve the first equation, I'm going to subtract 2 from both sides. So 3x equals 7 minus 2 is 5. I divide both sides by 3. X is equal to 5/3. Second one here, I'm going to subtract 2. I get 3x equals -7 minus 2 is -9. And then I divide both sides by 3. X is equal to -3. Now, when you're checking your work, you only really need to worry if your original problem was equal to a negative or if there's variables on the outside here. So because this is just equal to 7, it's not equal to a negative and there's no variables on that right side, we don't really have to check our answer. We know that both of these are going to work. So we get two solutions here. X equals 5/3 and x equals -3. So the key is the setup. You take the inside and then you equal to the outside and then the opposite of the outside. Are there any questions?
It's pretty simple to me.
They are a lot simpler than they may look.
So if, for
yeah,
example,
go ahead.
Yeah, if for example, it was equal to negative, so would be the same thing. For example, that we have that 7, it was like -7. Would be like a different. We'd be saying a -7 and 7.
Yes. So you'd set one of them equal to -7, the other one equal to 7, and it actually turns into basically the same answer. But in that case, you do have to check your answers because the absolute value always gives you positive. So if you have an absolute value equal negative, that's an impossible solution. And so then you end up with no solution at all. So that's why I said you want to double check about if it's equal to a negative, because an absolute value always gives positive. So if anytime it's equal to a negative before you split up your equations, then that means you have no solution. So because that's a negative, that's telling us, oops, let me go back to my pen. That would be telling us no solution. There are other questions. Okay. This is my last example. I know it's been a very long session. And this is definitely one where you have to check your answers because we have a variable on the right. And so we don't know whether our numbers are going to work out. So I've got a quadratic inside here. So once again, I'm going to be solving a quadratic equation. And this is going to be a little more work. So we have this absolute value by itself. And so first I write an equation, x squared plus 6x, and you just set it equal to that right side, 3x plus 18. When you write your second equation, x squared plus 6x, you change the signs of everything on the right, so because you're taking the opposite. So now it's equal to -3x minus 18. So you have it equal to the same thing and then the opposite of the same thing, so all the signs change. So now you have quadratic equations, so you need to solve by getting everything equal to one side. So the first, I'm going to go through the first equation. The x squared plus 6x equals 3x plus 18. So I'm going to subtract 3x from both sides and then also subtract that 18. I like to have a positive. So I'm going to get x squared, 6x minus 3x plus 3x minus 18 equal to 0. And let's see, this factors to x plus 6 times x minus 3 equal to 0. 6 times negative 3 is negative 18. 6 minus 3 is a positive 3. I set each of these equal to 0. So I have x plus 6 equals 0, x minus 3 equal to 0. And when I solve for x, I get x equals negative 6, x equals 3. Now, I need to check these answers. So I'm going to first start with negative 6. So in the absolute value, I'm actually going to run out of room here. I'm going to need another slide. So hold on, I'm going to temporarily stop sharing so I can add an extra slide here. So now you're going to just see the top of my head while I add this slide, because I'm definitely going to need another slide. Like, I'm not going to have room here. So hold on a bit. Okay. Now let me share my screen again now that I've added the slide. Okay, so I think what I'm going to do is I'm going to check these on the next side. Actually, let's solve both of these and then we'll check on the next slide. So I'll go through all of the solving here and then I'll write a note. Check on next slide, so I can do those all together. Okay, so now let's solve the second equation. We have x squared plus 6x minus 3x minus 18. So now I'm going to add 3x to both sides and add 18 to both sides because I want to have everything on one side, and I like positive x's. So I've got x squared, 6x plus 3x is 9x plus 18 equals 0. This also factors, so this factors to x plus 6 times x plus 3 equal to 0. So 6 times 3 is 18, 6 plus 3 is 9. So I'm going to set these equal to 0, so x plus 6 equals 0, x plus 3 equals 0, and then I get x equals negative 6 again, and x equals negative 3. So since we got x minus 6 twice, we only really need to check it once. So we're going to be checking 3, negative 3, and negative 6. So I'm going to move to the next slide and rewrite. We had x squared plus 6x equals 3x plus 18. And so we are let's first check x equals negative 6 to see if that works out. So I need to plug it in, so I'm plugging in negative 6. So I have negative 6 squared instead of x squared plus 6 times negative 6, close my absolute value, equals 3 times negative 6 plus 18. So negative 6 squared, that's 36, plus 6 times negative 6 is negative 36. And then on the right, 3 times negative 6 is negative 18, plus 18. 36 plus negative 36 is 0. So I get the absolute value of 0 is equal to the negative 18 plus 18 is 0. And 0 doesn't have a sign, its absolute value is 0. So 0 equals 0. That works. So x equals negative 6 is a solution. And I don't need to write it twice, so I'm going to just box one of them because it's there twice. Let's check x equals 3. So I'm going to plug 3 in for x. So that's 3 squared plus 6 times 3 inside the absolute values equals 3 times 3 plus 18. So 3 squared is 9. 6 times 3 is 18. And then 3 times 3 is 9 plus 18. So 9 plus 18 gives you 27. So the absolute value of 27 equals 27, and 27 equals 27, since the absolute value of positive is still positive. So that worked out. So x equals 3 is a solution. Now, I've already checked x equals -6. Now I'm going to check x equals -3. So x equals -3. So I've got my absolute value, -3 squared plus 6 times -3. Close the absolute value, equals 3 times -3 plus 18. So -3 squared is 9. 6 times -3 is -18. So I have 9 minus 18. Close the absolute value, equals 3 times -3 is -9 plus 18. So now inside my absolute value, 9 minus 18 is -9. So I have -9 in the absolute value equals, and then -9 plus 18, that gives me +9. Now the absolute value of a negative is positive. So when I take the absolute value of -9, I get 9. 9 is equal to 9, and that one also works out. So in this case, all 3 answers that we ended up do work in this absolute value equation. But they don't always do when you have that x on the right side, so you do need to check.
What happens if all 3, like only 2 out of the 3 work, and like one of them doesn't?
Then you just don't include it. I basically put an x through it, and you only write down or box the ones that do work.
Sounds good.
Mm-hmm.
So you say you just write the numbers. How do you write solution then? Like here.
I box my solutions. The other way you can do it is say x equals, and then you can put them as a set. You can write -6, 3, and -3, and you can do that instead, so that you can just put those solutions sort of in a set.
So it would be no solution when there's when you don't find the number can match equals to the number that absolute value that you have to the other side, right?
Yeah. So if you tried a number and it didn't work, then you don't write that down. And if none of them work, then there's absolutely no solution.
We put like x equals -6 and then x equals plus or minus 3.
Yeah, you could do that too. And some people don't even use the sets, and some people will just write -6 and then plus or minus 3 and write it like that, and that's fine too. Are there any other questions?
I think I got it pretty much.
Okay. So what I wanted to leave you guys with, and this is probably, I tried to make it, I was like, okay, there's this whole process. The key thing is that everything does eventually become linear or quadratic. And so depending, you have to identify the type of equation. And then I try to make this chart. So like I have at the start linear, you know how to solve for x. If you have a quadratic equation, your choices are factoring, completing the square of the quadratic formula. So I've kind of like put out how you could solve. Higher order polynomial, so that's x cubed or higher, your choices are to solve by factoring. And if you factor, you can either use a GCF or grouping. You can take roots, which I had an example of that, or you can do the substitution method, which turns into a quadratic. So that's why I have the quadratic following there. Then we've got the radical. So that was the ones with the fractions. And when you solve those either become linear or they become quadratic. So those always turn into one of those two. Our rational, or sorry, the radical I said was the fraction. The rational ones are with the fraction. The radicals, those are the square roots, cube roots. Those end up linear or quadratic. The fraction ones, those also end up linear or quadratic. And then the absolute value that you saw, those can turn into linear or quadratic. So basically everything eventually becomes linear or quadratic. So so the key is to kind of recognize which type of equation this is so you know what the steps are. And so let's say you know you have a square root, so that would be a radical equation here. So if you, when I share this recording, I'll also share the PowerPoint, so then you can go back to the part on the PowerPoint where I have the directions for solving radical equations. So that way you at least can say, okay, this is the type of equation it is. Here's the directions for solving. And then you can also see here are some examples. So I tried to kind of make a chart for you guys. And then that way you know where to go and then also to have the steps there. So yeah, you can kind of follow a guideline to help you solve. The key to solving is being able to recognize the type of equation and then following the steps. The steps are essentially the same. There's little tricks that could make things a little easier that come with practice. But you can basically follow the same steps every time as long as you know what type of equation it is. So are there any questions?
None for me.
How about you, Davis? Do you have any questions? Okay. I'm going to assume that's a no. All right, so thank you very much for joining me. I know this is a very long section, so it was a very long video in session because there's a lot to cover. But I'm going to try to get this video out and in your classrooms. I'm going to email it out to everybody. I'm going to try to get that out soon so that way you can re-watch it and, kind of watch things again if you need to. So thank you guys for joining me on a Saturday. I really appreciate it. And if you have questions later, you can send me an email or email your instructor if you have questions too.
Thank you. Have a great day.
You are welcome. You too. Both of you guys have a great day.